In this video, I will explain metal oxide semiconductor field effect transistor, generally known as MOSFET. This is most widely used electronic device in the world. Basically, it is used for designing of integrated circuits and designing of switching circuits, for amplification of electronic signals and designing of digital logic circuits, fabrication of memory systems like SRAM, DRAM, EEPROM, PLDs. And this is a very special application where mixed signal designing is used for analog and digital formats together. And this MOSFET comes from MOSFET family of field effect transistor. This is called metal insulator semiconductor, where semiconductor is insulated from metallic gate by using one insulator. When we use silicon dioxide as an insulator, this is known as MOSFET. MOSFET is also known as IGFET. This is insulated gate field effect transistor. General characteristics and general forms we can say about MOSFET is they are basically unipolar, only dealing with the majority charge carriers, and these are voltage control devices. And for this thing, easier fabrication process there. We use basically planar process where silicon on insulator processing is used, and they consume lesser power and they are of very small size. That means high density of fabrication is possible, where 4 to 5 million transistors can be fabricated on a single wafer. And MOSFET come in 3-pin or 4-pin packages. The 4th pin is basically for body or substrate. Rest of 3 pins are for drain, source and gate. In most of the cases, the body or substrate pin is electrically soldered to source. In some other lecture, I will explain body effect. Let me explain the operation of this device. For principle of operation of MOSFET, in fact, appropriate gate voltage with the consideration of polarity controls the current passing through the device. In fact, gate voltage controls and modulates the conductivity of the channel through the device, or the majority of charge carrier passing through them. It's a matter of transportation of majority charge carriers. Indirectly, we can say gate controls the current passing through the device, and that's why this device is also known as voltage controlled resistor. There are two types of MOSFETs. The very first one is enhancement type, the second one is depletion type. Let us consider the very first type, that is called enhancement type. These type of MOSFETs conduct at zero gate potential. When we apply a little potential between drain and source, there is no current. The reason is very simple. There is no conducting channel between drain to source, which has to be induced by applying appropriate gate voltage with consideration of polarity also. That's called inversion channel. Anyway, there are again two different types. This row indicate the symbols for N channel enhancement MOSFET, and this is for P channel enhancement model. And there are 4 terminals B and B and B. In this symbol, this B and S are interconnected, and this is a most modern symbol used for digital circuit designing, and drain and source are not mentioned, they are interchangeable. And one more important point is here, there is a broken line that indicates induced channel. A channel is to be induced by appropriate gate voltage depending upon the polarity of substrate and so many other things. I will explain in detail in next article. This is second type of MOSFET. It's known as depletion type. These type of MOSFET, depletion type MOSFET, conducts at zero gate voltage because there is a physically implanted channel between drain to source. Appropriate gate voltage with the polarity consideration can turn off the device And this device, depletion type MOSFET, can be operated in enhancement as well as in depletion mode. And these are the symbols. This is for N channel and this is for P channel. You see the reverse polarities. This is for N channel and this is for P type of channel. You see there is a difference. In enhancement type MOSFET, there was a broken line because there was no channel. That channel was to be induced. In this depletion type, there is a channel. And this thick line indicates there is a physically implanted channel already between the drain to source region. In this article, I will explain the basic construction of MOSFET. For this example, I am considering N-channel enhancement type MOSFET, N-MOSFET. The whole process for fabrication of NMOS, we are using a planar process. Basically, this is silicon on insulator technology. We start from P-type substrate. On this substrate, we deposit a very thin layer of silicon dioxide. On that layer, we again deposit a layer of polysilicon by using LPCVD process, low power chemical vapor deposition. Then masking is done on this layer to form the gate. Then remaining part of the polysilicon is etched further by using RI, reactive ion etching. It is done vertically, anisotropically to make regions for source and drain region. Then this gate section, gate region is used as an implant mask for doping source and drain region. See, one point is very important here. These two regions are abutted to gate edge. This is the part and this is the part. This is overlapping. This is overlapping. This is because of self-aligned gate technology. After that, this layer is further etched by using RIE, reactive ion etching, and to make space for making electrical connection for source and drain region by using sputter deposition. We deposit suitable material for electric connection over here. This way, the basic form is there. Let me explain the whole process by using very simplified model, three-dimensional model. And the whole block, we start from taking P-type substrate, and this is the layer for silicon dioxide, and this layer, the dark one, is polysilicon, selective masking for making gate, and these are electrical connection for, this is for source and this for drain region, and this is for body or substrate point. It is also here, the body part, and these are four terminals, this gate, drain, source and body terminal. In modern process, what we do is we take any substrate P or N, we coat thoroughly all sides this substrate with the nitride layer using low-cost technology. This is local oxidation of silicon. The whole substrate is all around coated with this layer. Then selective patterning, masking, metallization, etching and other subsequent processes are done sequentially to fabricate the whole device. Let us discuss operation of MOSFET. I am considering here N-channel enhancement type MOSFET, N-MOSFET. And this is the basic cross-section view of N-MOSFET. This is source region, this is drain region, gate, P-type substrate is there. I am considering case first when VGS is 0, no gate potential, we apply very small positive potential difference between drain to source. And this is at ground and this is positive. Now, there is no current flowing between drain to source. The reason is very simple. There is no conducting channel between drain and source. In another point of view, we can visualize there are two diodes, back-to-back diode. This is NP, this is NP, this is P part. Two back-to-back diodes are placed or exist between drain and source region. And in terms of energy diagram, we can draw this figure also. This part is source region N plus, and this part is again drain region N plus type. And the center part is substrate, where this is P type, and this is P and one diode, and this mount means there is a potential barrier for electrons passing from this region to that region. This is stopping the electron, rather transportation of majority charge carrier between source to drain region. That's why there is no current. The main problem is how to reduce this barrier. Now let us take case 2. When VGS is a little bit small, positive value. This is again positive. Now gate is positive, this is positive. The very first thing, this positive potential will repel all holes from here downward. All holes will move this way. That means it will create one depletion region this way. This is the boundary of depletion region just below this silicon dioxide surface. In the meantime, some electrons from here and from here, they will try to assemble here. And assembling of electron between drain to source region means the conductivity of this portion increases. And by applying positive potential, that means this potential barrier is reduced. This goes down. And this height reduces, potential barrier reduces by the application of gate potential. That means the whole device can be viewed as a gate controlled potential barrier. And reducing this height means this part, this region becomes less p-type but more n-type. And this is the situation which we call it inversion channel. Inversion. This was p-type, now it is becoming n-type. There is a level for VGS, one voltage, generally known as threshold voltage. This is the voltage required to induce sufficient amount of electrons over here. That's called conducting channel. This is called threshold value. When threshold value is applied here, so there is a real conducting channel, and that conducting channel, rather gate potential, is modulating the conductivity of this channel. When it happens, then current starts flowing between drain to source. And this is the diagram for current. This is the current and application of VDS. And this horizontal axis is the case when VGS is far less than VT. That means there is no conducting channel. The moment we are applying more voltage, much more than VT, for example 1.5, 2, we see current start increasing. And one important point we notice over here, the relationship between ID and VDS is linear. This is linear behavior, and this stands good only for a small value of VDS. And this region is called triode region or linear region, which we will discuss in detail in some next article. This is third case of operation of MOSFET, and when VGS is far greater than VT, VT is the threshold voltage for MOSFET. It is positive for NMOS and negative for PMOS. VDS is higher, large value is there. So I am considering only a restricted portion of that cross-section area of construction. This part is source, that part is drain, gate is there. We apply positive potential over here. And this is the property of metallic behavior. At every point you see same potential. That means the whole area is equipotential. Whereas this is 0 and this is at higher potential. We see between At these 2 points, there is a potential gradient. It is higher at this point, lower at this point. This is natural behavior of applying higher potential. One important point to be noticed over here, let us see the potential difference between the gate and at various points along the channel. The potential difference between gate at this point and between gate and at this point varies. It reduces across the channel. It is higher here, lower here. Higher here means the depth of conducting channel is more, and lower means the depth of conducting channel is lower. It is shallower here, it is having higher depth here. That means the shape is of tapered. Tapered shape, that means cross-section area is here reduced, here is more. Ultimately, the gate simply changes the shape, cross-section area of the conducting channel. Ultimately, the effective resistance of the conducting channel increases. That means conductivity reduces. What happens? It can be seen over here. This is current on VDS. For a small value of VDS, there was a linear behavior. The moment there is a change in shape of the conducting channel from rectangular to taper shape, that means resistance is increasing and conductivity is decreasing. That's why due to taper shape of the channel, current start decreasing. It is not following linear path. This is the reason, and this is because of reduced conductivity, because of potential gradient. One more point, you can visualize how it happens. This is the cross-section area, and this portion is divided into 2 parts. This is potential gradient, and the remaining part is conducting channel. For very small value of VDS, the shape of conducting channel is perfectly rectangular, and this is increasing, and this is the shape, intermediate shape, and this is taper shape. At one point when VDS is equal to VGS minus VT, we see the shape becomes a triangular. As a very particular case, this case is called pinch-off condition. At pinch-off condition, we see when VDS is equal to VGS minus VT. And this is the point over here. At this point, current becomes maximum, and increasing VDS beyond this point has little effect on the current, and current becomes constant. And beyond this point, this region is called saturation. Earlier I told you this part is called linear part, this part is called saturation part, and current remains constant whatever it was at this value, and this point is called pinch-off point, pinch-off condition. This is all about the shape of characteristic or output characteristic between ID and VDS. Let us see a total picture of ID versus VDS in next shot. This is the overall picture of output characteristic of N MOSFET, the relationship between ID and VDS, and this is the graph between ID, the current passing through the device, and current passing from drain to source region, and VDS is the potential difference across drain and source. So many curves are drawn here, right from taking from x-axis where VGS is far less than VT, that means there is no current flowing, no conducting channel exists. And the moment we are increasing the potential of gate by equal amount, for example 0.5, 1, 1.5 and 2.0, we see the scale of current increasing, and they are increasing. And the one thing is very important, the relationship between ID and VDS is not linear overall picture, and it is basically following a square law relationship for this reason, which I will explain in detail mathematically. That's why we see for equal increment in VGS, the gap between them is not unequal. It is rising. Anyway, this part from this line is line of connecting pinch-off points. That means for each value of VGS, for a particular curve, there is a point, it's called pinch-off point, and beyond this point, current doesn't increase a lot. Almost VDS has no control over the current. And this is the pinch-off condition for VGS, and this is the pinch-off condition for this VGS, and this is for this, and this is for this. If we connect all these pinch-off points, we see there is a line. Again, this line is following a square law relationship. And if we connect 1, 2, 3, 4, this is called line of connecting pinch-off points for various curves. And on the left side of this curve, this region is called triode or linear region. On the right side, beyond this curve, it's called saturation region. Almost these are parallel to x-axis, indicating the output resistance of the device is infinite. That's why there is no current increment with the increment in the VDS. No relationship, it's not controlling current beyond pinch-off point, which I'll explain in great detail. And this is the overall picture of output characteristic for MOSFET. For P-type MOSFET, everything will remain same, but the overall graph tracing will be in third quadrant. This is first, second, and third quadrant, because the polarity and direction of current will be reversed for PMOS.